Kevin, are you ready now?
Yeah, I'm ready.
Okay, let's get it started. So our next speaker will be Kevin Costello, who will talk about the vertex algebras and the self-dual Yang-Mills theory. Please.
Okay, thank you very much. And well, I'd like to thank the organizers for inviting me to take part in this wonderful workshop celebrating the career of Sasha Goncharov, whose influence can be felt in all over mathematical physics. So what I want to talk about is a subject that I'm just starting to get into, but that Sasha has made great contributions to, which is the structure of scattering amplitudes in gauge theory. So everything I'm talking about today is joint with Natalie Paquette. So what we want to explain is how scattering amplitudes of a certain cousin, simplified cousin of QCD, are correlators of an interesting vertex algebra. So what we'll find is the vertex algebra is a kind of vertex quantum group in that it's a deformation of a Cas-Moody algebra. So it's like a deformation of a vertex enveloping algebra. And our results, this is like our take on the celestial holography program developed by Andy Strominger and his collaborators. So our results are kind of closely related to things they've been looking at. So I'd like to start by reminding everybody what self-dual Yang-Mills theory is. So everybody knows the Yang-Mills Lagrangian, where I take f by star f. For self-dual Yang-Mills theory, shouldn't be a star there. We take a field which is, we introduce an auxiliary field, which is an adjoint valued anti-self-dual 2 form. What am I saying? I think I've written this really badly, sorry. Hope my slides in a bit of a hurry. E is omega 2 minus tensor G. So it's an adjoint valued anti-self-dual 2 form, and the Lagrangian is trace B wedge F. So this is a much simpler Lagrangian. And if we look at the equations of motion, we vary B to find that the anti-self-dual part of the curvature vanishes. That's the familiar ASD equations. That B is covariant constant. Now this self-dual Yang-Mills theory has been studied by many people. I think Chalmers and Siegel were one of the first. And it's related to ordinary Yang-Mills theory by adding on this term here. Once we add on this term to the Lagrangian, the two theories become equivalent in perturbation theory. Classically, we see that they're equivalent by, we take this first order Lagrangian, we perform a field redefinition like this, and it becomes the second order Yang-Mills Lagrangian. We know it now. So, as many people in this who have looked at this know, self-dual Yang-Mills theory is infinitely easier than QCD. For instance, it's a conformal field theory. So full Yang-Mills theory has a running coupling constant. So it's a non-trivial beta function. But self-dual Yang-Mills does not. It's a CFT. Well, it's non-unitary, but that's not that big a deal. Yeah. When we study QCD, there are QCD scattering amplitudes at every order in the loop expansion, and they quickly become completely intractable. Whereas for self-dual Yang-Mills, there are only one loop scattering amplitudes, and there's a very nice simple formula for them. Any computation you do in self-dealing mills, say you want to give me correlation functions, you only ever need a finite number of Feynman diagrams to do it. Well, the real reason you might be interested in self-dealing mills is that it captures certain leading order effects of full Yang-Mills gauge theory. For instance, suppose I wanted to compute correlation functions like this of certain components of the curvature. Because this field B goes like 1 over G squared F minus when I move from the first order to the second order formulation, we see that the correlation functions of this operator in full gauge theory, the leading term at this power of the Yang-Mills coupling are correlation functions in self-dealing Yang-Mills. So many people have liked to dream that maybe self-dealing Yang-Mills is completely solvable. So for instance, there's a paper of Losev where he suggests that self-dealing Yang-Mills is the simplest 4D CFT, non-trivial 4D CFT. I think I would more or less agree with that. So our interest is in scattering amplitudes of self-dealing mills and how they relate to QCD. So if we want to study UCD, we should take self-dealing mills and insert this operator trace B squared. So at 1 point in its weight, or 2 points in its weight, and so on. And here I'm just expanding the exponential. So this tells us that the scattering amplitudes of full Yang-Mills theory, well, we can think of those as scattering amplitudes of self-dueling mills in the presence of an operator, of this operator. I see various points. The technical term for scattering amplitudes in the presence of an operator are form factors. So, and it's a very formal automatic statement that form factors of self-dueling Yang-Mills compute certain scattering amplitudes of full Yang-Mills, up to 2 loops. That is like form factors with these operators. So, well. Okay, by the way, I would appreciate questions at any points because the way my Zoom is set up right now, I can't see other people, so I'm not entirely sure if people are following. Okay, so the thing we want to understand
But perhaps the question is if anybody has tried to compute some of these in this simplest for DCFT.
I have. I'm sure other people have too. It's not that easy. At least I didn't find it that easy.
Mm-hmm. So I mean, they're going to satisfy, I assume, the usual costing relations and things like that, conformal block expansion.
They do. Yeah, I'm not going to be. I think they do. It's not something I'm going to be talking about in this talk.
Mm-hmm. No, that's right.
Yeah. So the complicated thing is like unlike we're familiar with from 2D CFTs, like 2D chiral CFTs. There's a non-trivial matrix of anomalous dimensions in this theory. So the OPEs involve non-algebraic functions, which makes it kind of tricky.
Yeah, because it would be cool to have even just one example of a, an explicit 4-point function for DCFT.
I know. Yeah, absolutely.
Thank you.
Yeah.
Kevin, I have a Kevin, I have a question.
Yes,
I'm sorry, I came 5 minutes late. So I just
That's
want to
okay.
make sure. B is a self-dual 2 form, and you're perturbing an action trace of B.
Yeah, exactly. It's like
Okay.
trace BF minus plus
Okay.
squared Young-Mills.
Okay, thank you.
Expanding series in that. Exactly.
Yeah, okay, I got it. Thank you.
So this is something you're very familiar with. Yeah. So we want to compute scattering amplitudes of self-dual Young-Mills. Presence of an operator. And this is just motivation to say that for a carefully chosen operator, this is something that is really related to QCD. Oh, and before I go on, so what we'll find is that these amplitudes in the presence of an operator are correlators of a vertex algebra. And there's going to be some subtleties when we get to loop level at that statement. Okay, so I want to explain a little bit about amplitudes, but when I was first trying to learn about this stuff, I kind of got a bit hung up on understanding their notation. At least I found it a little bit difficult to understand at first. So I want to spend maybe 5 minutes explaining the notation people use in the amplitudes literature. So an amplitude has momentum, and we're working with complexified momentum, so the momentum is in C4. But the momentum is null, so p squared equals 0. So it lives in a conic. Now, as a representation of spin 4, C4 is a vector representation, is a tensor product of the two spin representations, S plus and S minus. The null vectors are precisely the decomposable tensors, which tells us that to specify a null momentum, I need to give you two spinors, one of each helicity, lambda and lambda tilde. So this is very elementary. Now, you might worry that if we're thinking about a gauge theory, we also need to specify, for a scalar field, that's all we need to do. But you might worry that for a gauge theory, you say, well, it's a one form, how do I describe that? But it's also described by the same data in a certain gauge. So to see this, a state is a solution to the linearized equations of motion. And I'd like to write them in a way where I haven't chosen a gauge just for the purposes of this talk. So really the important information is the two form dA. And this is two components, dA minus, which is really B for us, and dA plus. And each of those are closed. So I need a pair of closed self-dual 2 form and a closed anti-self-dual 2 form. Now, we can parameterize such by a pair of spinors as well. The way we do this is we remember that the space of self-dual 2 forms is the symmetric square of the spin representation. Same for the anti-self-dual 2 forms. And then the state of positive helicity, maybe I mixed up plus and minus here or something like that. I just take my exponential, my null momentum, I take e to my null momentum, and I build a 2 form from my spinors. If I want it to be self-dual, I use the lambda tildes, otherwise I use the lambdas. And you can check that d psi plus or minus, that these are indeed closed self-dual and anti-self-dual forms. So these give us the states of Yang-Mills theory. Now, given these states, you can form the scattering amplitude. And the amplitude is going to be a function of my momenta. So I'm going to input n states. Some of them are positive helicity, some of them are negative. And for each state, my momenta is parameterized by this point in S plus times S minus. And if I want to include the dependence on the gauge group, well, that's going to live in the nth tensor power of the dual of the Lie algebra. This map is going to be Sn, well, it's going to be covariant under a subgroup of the symmetric group. Okay, so this is what an amplitude is. It's also what a form factor is. It has the same structure. Now, typically, as we know from the work of Sasha, these are kind of interesting transcendental functions. But the things we're going to discuss in this talk are much simpler. They're rational functions. So the very basic one is, like the very first one might come across, is the Park-Taylor amplitude. So to describe this, let me describe the notation people use for spin 4 invariant functions on this manifold here. There's square brackets ij, where I take the inner product of the two spinors in S plus, and angle brackets ij, where I take the inner product of the spinors in S minus. And then the Park-Taylor formula is this expression derived in the late 80s, that at the tree level for QCD with two negative velocity states, we have this expression for the amplitude. Okay. All of this is so far as ancient history. So what I'm getting to is explaining how to interpret the Park-Taylor amplitude as a correlator of a CFT. So this follows in the direction proposed by Andy Strominger and his collaborators, called the Celestial Orography Program. And the way to think about it is as follows. Our amplitudes always have some homogeneity under scaling lambda and lambda tilde. So we can assume that lambda is in the projectivization of S plus, so it's in CP1. And then when lambda I approaches lambda j, there will typically be some singularity in the amplitude. And these singularities are really reminiscent of the singularities of a 2D CFT. So Strominger asked the question, do these amplitudes, are they the correlators of a CFT? And they give an affirmative answer for self-dual Yang-Mills when we consider only states of positive helicity. In this talk, I want to consider states of both helicity. So let's see an example. So because my lambdas are in CP1,
Kevin, I'm confused. I thought if they were all positive helicity, the amplitude is 0.
No, there's a one loop all positive helicity amplitude.
Oh, at one. Oh, okay.
One loop, yeah, exactly. At tree level, there's 0. That's the only non-zero amplitude.
That's what I was thinking. Okay.
Yeah. So let's do a really simple example. Let's choose coordinates on the CP1. So I write lambda equals 1, zi. And then my ij turns out to be nothing but zi minus zj, because it's the symplectic pairing. And then the Park-Taylor formula has this really nice expression. It really looks like the correlators of a vertex algebra. This observation was first made by Nair in the late 80s, when this was actually the starting point for many developments in amplitudes, including twistor string theory. So what we're going to do to start with is I'll build a vertex algebra so that all self-dual Yang-Mills form factors are correlation functions of the vertex algebra. So let me say why, to remind you why form factors. Park-Taylor amplitude It's an amplitude of QCD. But from the point of view of self-dual Yang-Mills, it involves one insertion of trace B squared. So the Park-Taylor amplitude is a form factor for the operator trace B squared. So here's the vertex algebra. We start by taking our Lie algebra, and we're going to add on a copy of the dual. This is the square zero extension, so the bracket of two elements of the dual is 0. And then at the classical level, there's going to be some interesting stuff about quantizing it. The vertex algebra is nothing but the Cas-Moody at level 0 for G plus G dual adjoin two bosonic variables V1 and V2. That means that the generators of the vertex algebra are currents for this infinite dimensional Lie algebra. So we can expand in powers of V1 and V2, and we find JA Mn. That's of spin 1 minus n plus n over 2, and J tilde, which is the dual representation, and is of spin minus 1 minus n plus n over 2. And these OPEs here, that's simply expanding out the sentence that it's the Cas-Moody at level 0 for this Lie algebra. Now, why would we want to build a vertex algebra like this? The reason is that the generators of this vertex algebra are in one-to-one correspondence with single particle states of the gauge theory. To understand this, we should remember a state depends on two spinors, one of which is lambda tilde, and the other of which we can write as being Z CP1, because there's some homogeneity. Now I can arrange my generators, J and J tilde, into series with these lambda tilde spinors involved there like this. And then we can identify them with the states of the gauge theory, where positive velocity states correspond to the J's, and the negative velocity states correspond to the J tildes. Just so. The way we do this identification, as you can see, which point on CP1 I'm inserting my state, my operator, that corresponds to one of the two spinors describing my state. Okay, so here's the first result. So we've built this big vertex algebra. So it's a very simple thing. It's a level 0 Cas-Moody for G plus G dual adjoin two parameters. The first result is that if we take the linear dual of factorization homology, so this sentence is the mathematician's way of saying conformal blocks. So the concept of factorization homology was developed by Bailenson and Drinfeld. And its purpose was to formalize conformal blocks. So the first lemma is that the linear dual of factorization homology is the same thing as the space of classical local operators of self-dual Yang-Mills as a representation of SO4 times scale. Okay. So how do we prove this? So this is a very mathy conference, so I'm going to give the, you can check this in many ways. It's really quite an easy statement. But the simplest way to do it, if you like the work of Bailenson and Drinfeld, is to say Well, they give a formula for the factorization homology of any kind of Casimir algebra whatsoever. So you just take our definition and you plug it into their formula. And they said factorization homology is the Lie algebra homology of something you get by taking the cohomology on CP1 with coefficients in Weisheva from the algebras. And then you look at that and say, well, that's the same thing as the coherent cohomology of twistor space with coefficients in the structure sheaf plus the canonical bundle, each tensor with G or G joule. And finally, you look back in the literature to the 70s by Ward, and you see that that coherent cohomology of twistor space gives you the solutions to the equations of motion, gives you the space of solutions to the equations of motion of self-Julian melts. So this result, you were simply putting together some classic results in the literature. It's very easy. Okay. Any questions?
Yes.
Mm-hmm.
So intuitively, if I have a local operator, I can look at form factors and they would look like correlation functions of the Carl algebra, I assume.
They wouldn't. Yeah, I mean,
they would,
like
because they still have rotational symmetry, and so is this the map? You think?
Yeah, I think so.
So you put the local operator and sort of look at which photons are gluons are cutting out of it.
Like, is this the map between local operators and formal blocks? Yeah, absolutely.
It's funny that the fact that it's an isomorphism seems quite striking. Do you think it's going to be true for more general theories, or is it special to?
I think it's really special to things which exist in twistor space. So, I mean, we're going to see, like we can see it already, and we'll see it in a couple of slides, that, if I have my vertex algebra, it's always going to have a really nice action of scaling, because any operator will have some specific dimension under scaling. Whereas in a CFT, my local operators can have anomalous dimensions. So it seems like you'd only have this when there are no anomalous dimensions. So it seems like a very special statement. That is, I certainly cannot imagine how one could possibly encode operators with anomalous dimensions in a vertex algebra.
Thank you.
Well, I have a related question. So is there a beta function in this theory?
No, there's no beta function in this theory. This is easy to see because the only Feynman, in the absence of any operators, you only see one loop Feynman diagrams at most, and any one loop diagram has as its external lines the A field. And then you think, well, a one loop beta function must be something built from the A field. The only thing it could be is trace f squared. That's a total derivative. So perturbatively, it's not possible to have a beta function. Perhaps there's something weird with the theta perturbation theory now. Okay. My slides got a little. You can see on the slide. Okay. So now we know we've identified factorization homology with the dual of local operators. Now, the point of factorization homology is, Valence and Drinfeld developed it, is it's the vector space where correlation functions live. If you look at their formula for the definition, it's defined so that if I give you operators at points, you get an element of this vector space. That's the universal recipient of correlation functions. Now, the dual of factorization homology will then be such that if I give you an element of the dual, you can define correlation functions, which are numbers. So what this tells us, if I have a local operator, I view it as an element of the dual factorization homology, you can use it to define correlation functions of the vertex algebra like that. So then I can take the correlation functions where I insert the generators of my vertex algebra at various points. But you can also use it to define form factors, where I insert various positive and negative velocity states with various momenta. However, we've seen that the generators of the vertex algebra, that's the same data as the states, single particle states. So once we've identified states with generators of the vertex algebra, the result is these are the same thing. So that form factors are the correlation functions of the vertex algebra, where the conformal block is built from the local operator I use to define the form factors. So at tree level, this is kind of the main result. So is this statement reasonably clear?
I'm actually confused why you have both a J and a J tilde in the angle brackets. Is that a misprint or?
Like here?
Well, say at the top line, you have a
At
J.
the top line. Oh, I just wanted to have, because in my vertex algebra, I have JMN and J tilde MN. And these correspond to positive and negative velocity states.
Right. So are you doing the maximum, the two negative velocity and n minus 2 plus positive velocity?
Well, like how many positive and negative velocity will depend on what operator you insert. So if you insert trace b squared, then at tree level, it will be 2 negative, number of positive. Basically, the number of negative velocity is how many powers of b are in your operator.
I see. And that's my other question. So I'm getting a little lost about whether these statements are about tree level amplitudes or are there loops? I guess you just said that there were only one loop diagrams at most.
Well, so eventually we're going to get to loop amplitudes. So
right now, these are only about tree level. These are tree level statements?
Right now, these are only tree level statements.
Okay.
Like there's going to be some difficulty which will require us to restrict to certain situations at the loop level. Okay, so I would agree that the tree level statements are kind of old hat, but I think it's still a fun state. It's still a fun way to compute tree level amplitudes and form factors. So let me demonstrate how this works. So the operator trace b squared. So this gives correlation functions of the vertex algebra. So I'm going to just write J for J00 in these expressions to save space. And then if you think a little bit about the symmetries of my vertex algebra, well, this guy it's like SO4 invariant. It's also dimension 4. You can kind of figure out what dimension various things in the vertex algebra are. You figure out just by symmetries that the 2-point function in this conformal block looks like this, where kappa is the killing form. So once you have that, you can use the OBEs to figure out what the endpoint function is. The endpoint function is determined inductively from the n-1 point function by the poles in the OBEs. And it's easy to see that you recover the Park-Taylor from that. So
if I remember your Lie algebra, your original Lie algebra had the J tildes. They were in the dual, and so they initially commuted in the absence of an insertion. Right? They had a non-singular OPE.
That's right, and you can see this in this conformal block. This correlation function has no poles.
Right. And so J and J tilde had a single pole and J and J had a single pole.
Exactly. So I mean, let me.
No central extension with the J and J.
No central extension. I mean, it can be a little space too. It can be fun to do the 3.1. So this is a sum of two terms where J tilde 1 over C2 minus C3 plus J tilde 1 over C1 minus C3, depending on where the J, there's a term when the J hits the second J tilde and has a pole there, or when the J hits the first J tilde.
Totally clear.
Yeah. And then that gives you this expression here. Okay, so let's get on to the more interesting stuff. Can this work at the quantity level? So if you're studying amplitudes, there's only one loop amplitudes, and they only involve states of positive velocity. So if you just focus on positive velocity states, then yes, it works. It works really nicely. And this was figured out by these guys, Bovara, Himwich, Pate, and Strominger. But we're trying to do something a little different because we want to look at form factors. And we want to use this identification of form factors with conformal blocks. And then it cannot work. So one way to see what cannot work is, which I mentioned earlier, and David asked a question. Self-dual Mills has no beta function, but it has an interesting matrix of anomalous dimensions. The first way it appears is if I look at, the SO4 invariant operators of dimension 4. There's two of them, trace B squared and trace F squared. And the matrix of anomalous dimensions looks like this. Now it seems there's no, I don't have like a formal theorem or something, but I just cannot imagine any way in which the conformal blocks of a vertex algebra would have this non-algebraic action of scaling. It seems impossible.
About logarithmic conformal field theory.
I thought logarithmic conformal field theory didn't have log OPEs. It more had like modules which braided around each other in some logarithmic way.
Well, it certainly has log of C1 minus Z2 and operating type expansions.
No, you could be right. I mean, it's more like log of the. It's more like a flavor symmetry. Classically, you have like a vertex algebra with a C star flavor symmetry, and that gets broken to, when you quantize it, logarithms appear. It just seems really weird.
Okay. Anyway. I mean, L is not the same thing as E1 minus E2, so I could be wrong.
Exactly. Yeah.
It certainly has the flavor. I mean, certainly has the flavor of logarithmic CO2.
I see what you're saying.
Any funny module instead of the.
Yeah. So that there aren't any funny modules inserted, but well, I think we have a better argument for why it can't work. So I think this is an argument for why. I think it's just a more solid argument, but it's more complicated. Okay, so if you think it's going to be a vertex algebra, then you should go try to figure out what the OBEs might be. And if you look in the literature about amplitudes from the 90s and later by Byrne, Dixon, Kosover, and Malin, and so on, Chalmers, you can find these really nice formulas for the QCD splitting amplitudes. And these are like one loop corrections to what happens when two particles become collinear. And now if you focus on the expressions that can appear in self-dual Yang-Mills, you can convince yourself that the vertex algebra should get this correction to the OBE. OBE where the 1, 0 part and the 0, 1 part should acquire a second order pole. And there's some particular constant, it's like 1/96 pi squared or something. But then you can ask, okay, does this define a new vertex algebra? And it does not. It's not associative. You look at the associator, get this particular associator, and you kind of churn through it. I'm sure people are familiar with the associator means I want to compare the 3 different contours. Like in that kind of picture. So you just compute the associator using this correction to the OBE here, and you find it's not 0. So there's another argument, I think it's more solid, that it's not possible to find that the one loop form factors of this operator are correlators of any vertex algebra. Right, so for us, everything came from twistor space, and we think of this as a manifestation of some anomaly in twistor space, which I might say a little bit about at the end. But that perspective tells us 2 ways of canceling this. If we take matter, some real representation, so that this trace identity holds, for example, G is SL2 and I have 16 copies of the fundamental, then we can get the story to work for self-Julian mills at the quantum level. An alternative method, which we've really focused on more, is that you stick with pure gauge theory, but you assume that this trace identity holds, that trace of x to the 4th is a perfect square. So this holds for the algebras SL2, SL3, SO8 are exceptional. And in these cases, we can add on a new field, which is kind of an axion. It's an axion because it couples to the topological term. But here we see it as a 4th order kinetic term. And then in these cases, we can also fix the problem. So I know that I think I didn't arrange my talk the clearest way, so this seems like it's coming from nowhere. But I hope you'll see at the end the origin of this. So what we can show by using twistor methods is that in either of these contexts, there is some vertex algebra which quantizes the Cas-Moody we started with, but we also add additional fields corresponding to our new fields in our theory, and that the same results hold. Conformal blocks of the vertex algebra are the local operators of the Fourier theory. The correlation functions are the form factors. So this vertex algebra, it's no longer a Cas-Moody. It has some OPEs which look like Cas-Moody's, but there are corrections which makes it look like a little bit like a quantum group. So I'll try to describe it, at least what we know about it, in these cases where I have the axion field rho. I mean, there's something similar in the matter case, but we haven't written down the description yet. So the way it looks is that we have these 2 things. These are from before. The J and J tildes corresponding to positive and negative Licity states. And E and F, and these are new from rho. And the reason there's 2 towers is that rho satisfies a 4th order equation. So it should be thought of as 2 scalar fields. Each scalar contributing a tower like this. And then from our twistor perspective, taking lambda g to be this constant proportionality in this trace identity, we can calculate what the OBs have to be. So I expect that, obviously you don't expect people to absorb this, but I just wanted to make it clear that something very explicit you can write down. Any questions? Okay. So let's write down some of the OBs involving J and J tilde. So by thinking just about associativity of the vertex algebra and using twistor methods, we're able to figure these out to some degree. Here we see what we had before. It's like a kind of Cas-Moody term. Here we see something really new where the OB involves a normally ordered product. Here we see the QCD splitting amplitude. And that's just forced on us by associativity. So what we find is that the associator we considered before, now it vanishes. An explicit computation of this associator shows, well, as long as the coefficients of these OBEs are what we said, and as long as the trace identity holds, then that associator vanishes. Now, we have a rather abstract argument for the existence of the vertex algebra, but I don't think we could say that I could give you a formula for all of the OBEs. I'd like to hope that the ones we have figured out are enough to determine everything else, but I'm not entirely sure yet. Okay, so so here's some features of the algebra. As I said, one of the terms looks like the QCD splitting amplitude found by Byrne, Dixon, and Costello. And if you're super careful about the coefficients of everything and the factor in how you match states to generators of vertex algebra, all those things, you do actually find the same coefficient they do. This kind of vertex algebra is not that dissimilar to things people have studied in other contexts. Like people have looked at the affine Youngian. It looks a little bit like a double affine Young. There's also an algebra studied by Nicholas Guay, and it's it's a bit like that, but with an extra loop. And other people were looking at similar algebras to Doherty, and I think partly joined with Schiffman, Rorgat, Musavin, and Joe. They were looking at similar things, but just for G instead of G plus G dual, but for totally different reasons. They were studying them because they were looking at the enumerative geometry of certain elliptically fibered Clavier threefolds.
Did you trying to compare it to an algebra of BPS states for any string?
Yeah. No, absolutely. I mean,
of a gauge theory. Right, so
I think I think you're right. I'd have a little difficulty making a precise statement in the version with G plus G dual, but certainly what these guys are doing is absolutely, they're looking at a coha of some elliptically fibered Clavier threefold. So it absolutely is an algebra of BPS states. I mean, it's really fun. Like they find something where the character of the vertex algebra is a generating function of BT invariance and this kind of thing. Things that you're familiar with. The G plus G dual case, probably there's some similar setup, but I don't see it yet. Okay, so far I feel like kind of asserting this vertex algebra exists based on twistor methods. That's a bit of a black box. So I want to give you a few more concrete things. So here's another fun computation you can do. So the Park-Taylor amplitude is, of course, really simple. Here's one that's a little more complicated. So this was first computed by G. Mall, and it's the one-loop all-plus amplitude of self-dual angles. Now, once I add the axion, there are no amplitudes whatsoever. So to get this amplitude, I need to insert an operator which has the effect of removing the axion. So if I look at my Lagrangian, if I insert this operator, that will have the effect of removing any axion exchanges. So you would expect that the form factor of this operator here, in our theory, is the same as this one-loop amplitude. Now, according to the prescription, we got to go find the conformal block corresponding to that form factor, and then compute the correlation functions. So this you can do.
Kevin, isn't it amazing that you can have one loop and rational functions are the answers? I mean, don't we expect, I think you said at the very beginning, we expect, normally we would have transcendental functions, polylogarithms and so on. How in the world does a one loop amplitude give you something so simple? Is there? I know that's not a very sharply formed question.
No, I know what you're saying, right? Because
it's kind of amazing.
It is kind of amazing, and there's.
I mean, it's obviously the self-dual nature of the theory, but I'm just kind of astonished by this result.
No, I mean, there's a paper by the kind of Byrne, Dixon, Costello guys called like the last of the rational amplitudes or something, where they list all of the amplitudes in QCD that are rational, and they go up to one loop with one negative velocity particle, I think, and after that they become irrational. What seems to happen in practice, like anything we're going to compute from the vertex algebra is going to be rational. So you can list all of the amplitudes, which can be written as form factors in the presence of a single operator. And I think they match exactly the rational QCD amplitudes. So I would say that's the explanation. So for instance, if I had a single trace b squared, to this add one loop, this is also rational, but incredibly complicated. Gee, this is what I have the next slide. Okay. So these guys, Alan, Byrne, Chalmers, Dixon, Costello, also computed these one loop, one negative velocity. So these correspond to self-dual and Mills plus one copy trace b squared. And it's some incredibly complicated thing. Like I've just copied and pasted a formula for the 7-point amplitude. And I don't even know if they have closed form expression. I'm not sure to what order they have a closed form expression. However, we can do the same thing. Like if we're in the case where the anomaly cancels, either by using an axion or by using appropriate matter, we find it an incredibly simple formula to have written on the bottom. So our approach implies there must be some incredible cancellation. So if you take their amplitude, it's some rational function of a bunch of variables. And to compute the full amplitude, we must multiply that rational function by the color factor, where I take the trace, the adjoint by this trace in representation. And the claim is that as long as this identity is satisfied, everything, a bunch of terms cancel here, and it becomes something much simpler. So I kind of want to go and check that directly rather than by using our twister method. But this is a very concrete consequence of our approach. So in the last 5 minutes, I just want to quickly explain why this comes from twistor space. So the Penrose-Ward correspondence states that self-dueling Mills comes from holomorphic BF theory in twistor space, something really quite similar to what Davide was studying. This turns out to be false at loop level. The reason is holomorphic BF theory in twistor space has a gauge anomaly. So this diagram here, this box diagram, is not gauge invariant. The gauge variation looks like this. So if I want to see why this anomaly occurs, it's a local thing, so it then takes the same form at all free folds. So you can write anomalies in terms of the curvature of a determinate line bundle, which you can then compute by the Groth and Dieck-Riemann-Roch formula. It'll be the integral over x of the fourth Chern class of the adjoint bundle plus this other term involving the Todd class. Now the Todd class term doesn't appear on twistor space, but this term here involving the fourth Chern class of the adjoint bundle appears on any geometry. Alternatively, you can think about things by dimensionally reducing to more familiar systems and dimensions, complex dimension 1, where there are very well-known anomalies. But the axion story comes because this can be cancelled by introducing a new field, which is a 2-1 form. It couples in some particular way, and it cancels the anomaly by a Green-Schwarz mechanism. So this is something, it's a variation of something I developed with C. Lee. And this field eta becomes the axion in O4. So the claim is really that the failure of associativity we found on the non-trivial matrix of anomalous dimensions, they can all be traced back to this anomaly in twistor space. That when I introduce an axion, they all go away. And then finally, there's a very formal argument involving something we call causal duality, which builds the vertex algebra from the holomorphic QFT in twistor space. Again, this step is not dissimilar to what Davide was explaining. So that's how we know the vertex algebra exists. What its generators are and how we can compute some low-level OPs. I still don't think we have complete control over all of the OPs in the vertex algebra. Okay, so I think I'll stop there.
Thank you very much. Are there any questions? Please speak if you have questions. Maybe I have a very naive question. So it seems in the last constructions, there is something very similar also happening in cluster theory. So I was wondering if you see any construction of cluster algebras in this story.
I don't, but what's the similar thing that appears in cluster theory?
So there is like, I don't know, there's Greek relations, like Ptolemy relations. So if you have some tree and then you can mutate this in the other direction.
No, there might be a connection, but I don't see it.
Okay. Yeah. Any other questions?
I have one.
Please.
Mhm.
So it's not so directly related to your talk, but you did mention the celestial holography, the celestial amplitudes. So so that means you've thought about this carefully. So something that I find very puzzling about the proposal of Strominger et al. Is they define these celestial amplitudes by some kind of integral transform in energy space. Right, they choose a direction and they sort of integrate overall energies with that same direction. It seems totally unclear to me that these amplitudes that they define, when you actually look at their definition, are going to be correlation functions in a local quantum field theory. And I understand that, you know, in some special cases, they get these nice formulas that like vertex operator algebra expressions. But, you know, for the general amplitudes that they define, it's totally unclear to me that those are going to be correlation functions in some local two-dimensional quantum field theory.
Mhm.
And, you know, when I press them, you know, I start to learn that, you know, if I have enough operators on the sphere, I could start to have singularities when two operators come together, but that involves some faraway point. I just wonder if you have any thoughts on that.
Well, I suspect Andy and I have quite different perspectives on this. My thinking is that being able to present amplitudes and form factors as correlators of the vertex algebra is a hint of some kind of integrability. For me, the whole story is really quite similar to the integrability in two-dimensional theories, because here we started on twistor space with some holomorphic theory and moved down to all4. The twistor line appeared as some kind of spectral parameter. And it's very, very analogous to the way you could start with, you know, partially holomorphic four-dimensional Chern-Simons theory and dimensionally reduce to an integrable theory in dimension 2.
Oh, I see. That's okay.
So yeah, so my interpretation
is different from what Andy is doing. I just was really asking a question about celestial.
Well, yeah, I don't, yeah, there's lots I don't understand with what they're doing. I mean, I don't understand, lots of details I don't understand. Things match very nicely. You know, they do the Mellon transform and they find explicit expressions for their amplitudes. And those are really natural things in twistor space as well. They're just polynomials in some of the variables. So, but there's, yeah, still lots I don't understand.
Any other questions? Okay, so if no more questions, let's thank the speaker again. We will resume at 3:15. Our next speaker will be Eric Zaslow.
Hi, Lin.
Hey.